Hello, everyone, and welcome to a Quantum Mic Classic episode. For those who don't know, the Quantum Mic, prior to being a YouTube video, was actually a podcast that I did during the COVID-19 period, where I did some interviews with people who were involved in physics, most of them physicists themselves. So, since I'm very busy right now, I thought it would be fun to bring these back and allow you to listen to them here on YouTube. So, that's what this video is. Today we are going to be doing my first interview, which I did with Dr. Jeff Lange about electronic warfare. So please plug in those earbuds, and I hope you enjoy. Hello, and welcome to the first episode of the Quantum Mic. I'm your host, Owen Darragh, and today we are talking to Dr. Jeff Lange, who's a senior defense scientist at the Department of National Defense. Thank you for joining me today, Dr. Lange.
Hi, Owen. It's great to be here.
So how about you introduce yourself?
Sure. As you mentioned, I am a research scientist for the Canadian Department of National Defense. I received my my undergraduate degree in applied physics at McMaster University. Then I went on to the University of British Columbia to do my graduate work, including a sabbatical at the University of Melbourne. I joined the Department of National Defense in 1997, where I've been employed in the field of electronic warfare ever since.
That's very interesting. What was it like doing your PhD at the University of British Columbia?
My graduate work was actually one of the most interesting times I've had as a researcher. What I found in my undergrad is there were a bunch of people. We were all kind of coming together, but we didn't really get to know each other until the second and third year. Whereas when I joined for the master's program, there was a small cadre of us, and we were together from day one. It was a really exciting time because we had condensed matter people, we had theoretical physicists, we had people doing subatomic, which was my field of expertise, and a few other varieties of physics. And it was great. Very synergistic time. We fed off of each other, helped each other out. It was a really worthwhile, rewarding time. I got exposed to and I got to work with some leading experts in my field, and really galvanized my interest in doing science as a career.
Oh, so what sort of, you said you focused on subatomic physics, right?
That's right.
Okay. So was there any particular area of subatomic physics that you studied during your graduate years?
One of the reasons I went to the University of British Columbia was the opportunity to work at Triumph, the Tri-University Meson facility, which is on the UBC campus. That area of research is lower energy, so you're looking at particles interacting with the nucleus and meson physics, as opposed to more high energy fields such as at SLAC or at CERN in Europe. Although we certainly had people that were working in those collaborations as well. My work was more in the lower energy field. As great place to work, got my hands dirty, doing electronics, stringing cables, trying to troubleshoot all kinds of electrical errors and logic problems. It was a fun time.
That's really interesting. So how did your graduate work lead into you eventually working at the Department of National Defense?
To be honest, it did not lead me to my current job. That said, it prepared me immensely well for it. My father was in the Air Force, so I grew up in and around the military. And I had a summer job in Halifax doing underwater acoustics. So from that, I always had it in mind to join the department as a full-time researcher. And about the time I was graduating, there was a hiring campaign on, and put my application in, and was very lucky to be picked up. I can say that the time I spent learning how to lay out an experiment, to do the troubleshooting, selecting the data, understanding how to analyze it, how to report it, how to do the analysis and the supporting simulations have all been instrumental in my career with national defense.
Okay, so speaking of your career at the Department of National Defense, what sort of physics are you now doing there? You said that you are working on electronic warfare, correct?
Correct.
Okay.
So I would have to say I'm in the field of applied physics now. Actually, a lot of what I do is more closely related to electrical engineering than to subatomic physics that I studied. But again, the skills that I learned doing physics prepared me extremely well for what I work in. So, for those who aren't aware, electronic warfare deals with the propagation of electromagnetic waves through the atmosphere, and also we work to understand how electrical signals are processed with equipment and the effects of electromagnetic radiation on electronic equipment.
Okay. Thank you for that summary, actually. That's very helpful. Can you give any examples of what you're currently working on? I understand that the Department of National Defense likely working there limits the amount of information that you're allowed to give, but is there any examples that you would be able to supply of sort of what you're doing now?
So my work right now, I look to understand how electronics work and how we can get different types of electrical equipment to perform the way that we want. So for me, I work in radio electronic warfare. So we're dealing with signals in the 1 to 15 gigahertz or so, that kind of region. So we're talking about radar systems, we're talking about sensors, such as radar warning receivers. Um, so when our ships and our aircraft go out in the world, they want to understand what kind of signals are out there. They want to understand whether they're being encountering signals and waveforms from friendly forces or adversarial sources. And if so, can they understand what the adversary is trying to do? And that will inform our forces of what's going on so they can take appropriate actions.
That's very interesting. I'm going to loop back actually to what you said before about doing more electrical engineering. What sort of branching between, as someone who studied physics and particle physics and applied physics, how does that sort of loop into what you're doing now, which is more around electrical engineering?
So, a lot of what I look at is the performance of electronic devices to new types of waveforms. So, I will do studies on uh, different electrical waveform constructs, um, playing with phase coding, playing with timing properties. Um, and for those who are familiar with Fourier transforms, if you make an adjustment in either the time or the frequency domain, there are spin-off effects necessarily in the other. So it's not always straightforward, but sometimes you can kind of come in and affect one thing and get a spin-off in the other that was either beneficial to you, hopefully, or it creates an adverse effect that you weren't expecting. So I do a lot of work trying to understand that area and the effects of different signals on different types of electronic devices. And then the military, the Air Force in particular, in my case, will take that research and will apply it to their own particular engineering needs. And I'm also involved in that process, but that's more of in a supporting role.
Okay. Could you actually explain a bit more about what the wavefronts are for those who are listening that don't exactly know uh, the form of lingo?
Sure. So the easiest thing to think about is either a bat or even a dolphin, um, who use echolocation. And it's the same principle as a radar. So a bat will sing a song and will have certain characteristics, and that will go out, bounce off anything that's out there, and come back. Now, the bat's ears are going to be listening to its own particular song. So, the frequency that it listened to, and if it put any modulation on it, so if it just goes out as a single tone, or if it throws a little change in tone in it, or whatever. Um, Radars work in the same sort of way. And the changing of the tone would be something that you could do to make your signals more easy to pick out against all the other background. And when you're looking at your signals, you're also looking at things like the timing of it. So, how far did the signal go out and come back? That indicates distance. You're looking at Doppler shift. You're looking at, again, the frequency structure. And then there's all kinds of pulse processing that goes on. So, way back in the day, you'd send out a pulse, take the pulse back, and that was it. But now you have devices that will listen for a time, get a whole bunch of signals back, and try to add everything up. And if everything is coherent, it all adds up linearly. If it's incoherent, like a random noise signal is, the signals kind of even themselves out. So you get that sort of pulse processing that goes on. We deal with amplifiers, which are nonlinear devices. So they have a nice clean linear region, but um, if you get if they receive a signal that's outside of their linear region, they're going to have different effects. So part of the work that I do is understanding where those linear regions are, and if they detect a signal or a waveform that they're not designed to, what are the adverse effects of that on the performance of the device. And as you can imagine, for our men and women in uniform, when they're going out and doing their job, they want to understand um, where their equipment will work and where it will break down, so that they can conduct their mission safely and come home.
Of course. That was very informative. Thank you very much for doing that little summary. Have your time at the Department of National Defense ended up leading to you working only with scientists within Canada, or have you had to work internationally?
I've been very fortunate that I can answer yes to both. Um, my branch of the department has offices across the country. We've got people in Alberta. We have a very small footprint out in the West Coast. We also have labs in Toronto, Valcartier, which is just outside of Quebec City, and also in Halifax. And I've been fortunate that I've been able to collaborate with people with a lot, with a very wide span of research interests throughout my years. I've also been fortunate to work in a number of international collaborative forums. The two most prominent are NATO, which I'm sure will be very familiar to your listeners, and also something called TTCP, which is the Technical Cooperation Program. For those who are interested in defense affairs, may have heard of something called the Five Eyes, which is a collaboration between Australia, Canada, New Zealand, Great Britain, and the United States. And there are a number of memorandums of understanding and project arrangements between these like minded countries. In my own case, the relevant one is TTCP, and that's an arrangement where the research branches of the various defense departments get together and do research. Quite often, and more so as we see the advent of artificial intelligence and quantum computing coming in, there are vastly new areas of research to be undertaken that are honestly beyond the scope of most countries' willingness to invest. Um, so we do find it quite helpful if we can get together um, from the different nations and pool our ideas and pool our resources, and we can advance the work that we're mutually interested in much faster, um, working together than we can apart. So I've sat on a number of TTCP panels. I've sat on a NATO panel, research panel, and it's been very interesting. You get exposed to completely new approaches to the work that people develop because they've got different operational paradigms, and it's very rewarding.
That's really cool. Are there any particular panels that you found the most interesting to work on?
Yeah, there's two that come to mind. One's NATO, one is TTCP. The NATO one was looking at uh, the ability of militaries to use passive tracking to follow aircraft. So, passive tracking is where you are listening to emissions only. You're not actually broadcasting anything. So, if we return to the example of the bat will send out a signal, you'll sing its song and listen for the reflections. That would be an active transmission because it's singing. If it was operating passively, it would be listening for the reflections of the songs coming from another bat and staying silent. So in this application, rather than having a ground based radar like an air traffic control radar or ground control intercept or what have you, sending emissions into the air and listening for the reflections of aircraft. Um, Certainly in Europe, what's happening is are listening to the reflections of aircraft coming from broadcast signals from television stations or radio stations and listening silently to um, locate an aircraft and form a recognized air picture. It's a very different problem set, and that was very interesting to work with. On the TTCP side, um, traditionally, a lot of the hardware, certainly military hardware, is all hardware based. So you're talking about tubes, you're talking about cables, you're talking about chips, capacitors, that sort of stuff. Now, with a lot of capability is being done through FPGAs, and we were investigating the feasibility of migrating these larger scale pieces of electrical equipment, and can we migrate them down into a chip? So trying to understand that sort of revolution in military technology and then understanding the implications for electronic warfare. It was another very rewarding experience. And it's something that has been feeding my research to this day.
That's very interesting. Thank you very much for being able to share about that. And thank you very much for having come on. Now, we're coming near the end of the time limit, so I'd like to just take a moment and ask you, is there any particular experiences throughout your whole time doing science, studying physics, that jumps out to you that you found was either the most memorable, most influential on your life path, or just any important moment in particular that you found?
Yeah, I'm trying to. I've been fortunate. I've got three instances. Um, First is I was able to get an exchange to Australia. So I spent 2 years at the Defense Science and Technology Organization, as it was known then, doing collaborative research, and it was good because I could bring down our approach and learn the Australians' approach to what was then a new problem area for us. Um, and we had done that in exchange, and because at the same time, Australia had posted someone up to my lab. Um, so it was a very fruitful exchange for both our countries. Um, The other one that comes to mind was we're having we're trying to solve this one rather hard nut of a problem, and a bunch of us in the lab were sitting down together and trying to figure this all out. And the more we talked about it, the clearer it became that not any one of us, had enough information to solve the problem. So we ended up convening a series of workshops within the country. And over the course of about 2 years, the entire community of practice, from out in Cold Lake in Alberta to Valcartier in Quebec City, down to Trenton, Kingston, the Royal Military College, we all convened and we were having discussions and trying to understand the problem. And we made a lot of progress out of it. A lot of people that participated referred to the Solvay conferences in the early 1900s of just bringing the community of practice together and whiteboarding everything and just trying to figure out our problem space in a relaxed way. And I have to say that collaboration was one of the most memorable highlights of my career.
That's very interesting. Well, that's all the time that we have for today. So thank you very much for coming and joining me, Dr. Lange. It was a pleasure to have you on the show.
It was great being here.
Thank you for listening to this episode of The Quantum Mic. Join us next week for our first episode of Relative Greats, where we learn about Galileo Galilei, the Italian astronomer who helped lay the groundwork for modern science. You can follow The Quantum Mic on Twitter at quantum_mic to stay up to date with the show. Let us know how we did by leaving a review and subscribing to our show. This episode of The Quantum Mic was hosted and produced by Owen Darragh. Episodes were edited by Owen Darragh. The Quantum Mic podcast was created by Owen Darragh, and the music used in this episode was created by Kevin McLeod. Thank you for listening, and we'll hear you next time on The Quantum Mic.